I am Brandon Romero, and today I will be sharing my work with Hao Feng, Polka Agua, and Edward Elson on EyeSight hand, design of a dexterous robot hand with vision-based tactile sensors and compliant actuation. So there's this common frustration with robotics today, where if we compare a human performing a task such as simply pick and place versus a robot, what we see is that the robot still is kind of stuck in this paradigm where it slowly approaches an object, and then it kind of carefully grasps the object before moving it to its place location and then slowly in place. And we contrast that with the human, and you can see that the human is just very quick, very reactive, and very robust to all of the interactions that it has with the environment. So the question that we began to ask is, what is the thing that's causing the gap between a robot actually performing like a human does at these kind of tasks? If we kind of look at the state of the art in robotics, we're in this situation where even though a lot of time has passed, robot manipulators still follow this kind of classic paradigm of the original industrial robots, where they're designed to be exactly precise. And so what they do is they rely on actuators such as like harmonic drives or these multi-stage gearbox, which are, very inefficient. They're very hard to backdrive. So if it was to collide with the environment, it would kind of have this rigid reaction. And then even if they were backdrivable, in some instances that they are, they're so highly geared and the reflected inertia of an actuator scales with n squared even when it did make impact, that would result in high contact interactions, which could actually damage the hand or damage the environment itself. So robots are kind of stuck in this kind of behavior where they slowly approach the object to reduce the likelihood of those type of impacts. But there's more to it. When we look at humans, even though our hands are compliant, our actuation is compliant, what we're also relying on is like this rich sensory information from tactile sensing. If we inject an aesthetic into someone's hand and we ask them to perform a task, that loss of tactile sensation to kind of understand what contact forces are happening make it very difficult for a human to perform the task. And so, like, if we don't equip robots with tactile sensing, like, how do we expect them to also accomplish tasks? And of course, there are a multitude of tactile sensors being integrated into um, dexterous hands, but they fall into like two categories. Either they're, you know, estimating the contact range, like on the left example, or they're creating a contact map with some kind of pressure sensors, pressure sensitive array. But besides actually determining contact interactions, one of the fundamental problems in robotics is this problem of occlusion. As a robot approaches object, it's going to cover the object, and if you imagine you want to work on more precise tasks, there's going to be more occlusion. So, like, let's just have a thought experiment where we have a screw, like an M2 screw, and we ask a robot to go and pick it and then do some in-hand manipulation. So the robot hand goes in, makes contact, and if we just have like just a full torque sensor at the end of the finger, uh, if you were to ask, "Oh, where are you making contact on the screw?" You won't be able to tell because you just have this single scalar value or this value that doesn't really tell you any geometric information. If we go up to 4x4, which is kind of reasonable for a lot of tactile sensors out there, you see it's still really hard to tell where the robot's touching. Let's scale it up. Like 10 by 10 is where more of the state of the art tactile sensors on dexterous hands are, and it's still very difficult. 20 by 20, we're starting to see like where we are, but not 100% sure. And then let's just go ahead and go to like 256 by 256. At that point, it's extremely clear that the robot is making contact with the thread of this group. And so in this work, what we want to do is we want to address these two problems of compliant actuation and high resolution tactile sensing and integrate it into a single package. So we introduce EyeSight hand. And just as a teaser, here's an example of using the EyeSight hand for autonomous task of opening a ketchup bottle that's not fixed to any surface. Kind of showing that we're able to do these really contact-rich manipulations. Let's go ahead and dive into the details. We're going to cover two parts of the hardware, actuation and tactile, and then finally we'll talk about how to make it autonomous with multimodal learning. So in terms of actuation, we really wanted this compliant and reactive behavior. And we've seen a lot of legged robots like the Spot Mini and the Unitree robots. They're very reactive. And, what they rely on is these quasi-direct drive actuators where the gear ratio is low enough where the reflected inertia is low and it's easy to backdrive these actuators. So what we did is we put a lot of effort into actually making it so that if we had a dexterous hand that's the size of a human, we can actually incorporate these type of actuators into this package. And so you can see similar dimensions to my hand, and then kind of the actuator architecture where we only rely on leakages or directly driving the output, so that's kind of robust compared to tendon-based robots. And this is really beneficial because we get that reactive behavior where we can just run into the environment and the hand will react. You can see it can quickly pick up this banana. You can see all the contact interactions that are happening. And despite that, the robot's still successful and there's no damage to either the robot or the environment. And when we compare it to soft actuators or soft hands, which people always say are compliant, the problem with those type of designs is if we had a heavy object like 2 kilograms, it would be hard to do like in-hand manipulation like we did here with those kind of manipulators. So we get that compliance as well as the rigidity and the strength of having conventional actuators in a robotic platform. In terms of tactile, of course, we went with a vision-based tactile sensor. It's really high resolution, where you can see all of the intricate information of the Oreo, as well as dots on the surface to give you shear and force information. And what we wanted to achieve in this design was two things. First, in this design, we have atactile sensors. And as we scale up to more dexterous hands, we have to really figure out how to minimize the data transfer. Because post-processing can be like really detrimental to the reactivity of your gripper because it can increase latency and so forth. The other thing is that simulation is continually becoming like this important tool in the toolbox of robotics. And so there are vision-based tactile sensors out there, but they're kind of difficult to simulate quickly and easily. And so we wanted to make a design that addresses both of these questions. So what we ended up doing is, looking inside one of the fingers, we have a cob LED, which illuminates a diffuser and evenly distributes overhead lighting onto the sensing surface. And when we look deeper into what the sensing surface is, we have this semi-spectral material, which just means that we have like these tiny little aluminum flakes that act as mirrors. And since there's kind of like these discrete mirrors, um, they reflect light in a direction, but they're partially diffused because of the different angle. And this is beneficial for two reasons. If we look at the simulation pipeline of a tactile sensor today, a vision-based tactile sensor today, first you have to calibrate the direction of the lighting and then figure out how to do the computation for the shadow mapping. Then you have to figure out the deformation of the sensor, and then you have to model the bidirectional radiance field to actually see the optical response. And if we have a conventional EyeSight, like on the left, this directional illumination is problematic because to actually do shadow, so you have to either like perform some kind of costly operation like ray tracing. But with our sensor, you can see that there's no shadows being casted, and so we can get rid of this timely calibration and timely computation, and just rely on the deformation of the sensor and modeling the bidirectional field reflectance function. And so if you look at these two sensors, one of them is simulated and one is real. Um, and the way that we do it is, we can use just a simple MLP neural network to actually render the contact based off some kind of rasterization of the sensor. And so given some kind of like a deformation model, such as FEM, you can go ahead and simulate quite realistic optical responses from this method. So finally, moving on to multimodal learning, we benchmarked on 3 tasks. The first task, as you saw in the teaser, was opening a ketchup bottle not fastened the table with one hand, kind of showing the importance of this impedance control and compliant actuation because you don't really know the precise location of the hands to open it. The next task is this task of given 2 plates, slide one plate off the top, pick it up, and then gently place it next to the previous plate. And then lastly, we have the task of using tool usage and seeing like this stringent contact, which is commonly associated with dexterous manipulation, where we have a knife, we pull it out, and then we cut a kind of rigid plasticine object with a knife, just in half. So for each of these tasks, we have a standard action chunk and transformer architecture for imitation learning. These consist of three different inputs, one of a global camera, kind of close to that ecocentric view, a wrist camera that has a fisheye lens, so it can see the entirety of the hand, and then we have eight tactile images. Given this architecture, we perform 100 demonstrations of each task, and kind of to see whether or not the tactile sensing is actually beneficial for these tasks, we do two policies, one that's vision plus tactile, and then one that's only vision data. And the thing that we want to kind of see is the emergent behaviors of these two models, especially in the tactile case. So for the bottle opening case, the important thing that happens is like without tactile, the thumb needs to catch a bottle, and the robot actually has difficulty making contact in the right location and actually lifting up the lid. It kind of misses and it just fails at opening the lid. The other thing is contact force regulation. Um, you have to have this constraining force, and if you don't have proper constraining forces, the object's going to be pushed when you try to open the lid. For tool usage, one of the important things is, you know, actually detecting this extrinsic forces, and this illustrates one thing first. In this first example, when we try to cut, uh, the robot only partially cuts the object because the object's partially occluded in the camera by the knife. And so the robot only partially cuts, but with tactile sensing, it's able to disambiguate when it's cutting object versus when it's making contact with the cutting. Another example that's kind of really illustrates the use of extrinsic contact sensing with this hand is, the use of the tool could lead to excessive forces. And, since the vision-based policy doesn't really know what contact forces are being applied, it really applies too much forces and displaces the board. And then for our final task, kind of emergent behavior that we see is two things. One, again, like this contact force regulation, where the robot is not applying enough force to actually make the plate slide. And since it's a robot, it's just like going to sit there and it's going to continue to try to like slide the plate, make contact, slide the plate. And then unfortunately, it just sits there forever. Um, and kind of the next example that goes into this is like one of the things that people commonly associate with tactile sensing is this detection of slip. So even though the robot is just able to actually slide the plate this time, once it actually tries to pick it up, these are heavy plates, they're just normal plates. And when it tries to place, what happens is, it slides out the fingers because it's not applying enough gripping force. And so what we can see is that by including vision and tactile policies versus just only having visual data, we achieve quite a significant improvement in your policy evaluation, where yes, the success rate goes up from 50% all the way to 30%, kind of underlying the kind of crucial role that tactile sensing plays in contact rich manipulation. That's it for the presentation.